all those fun things. All right. Before we do that, though, I want to go over a very nice visual related to these integrals or antiderivatives that we've been using, as well as this first fundamental theorem of calculus. So if it's okay with Anuj, because he's the one that came up and showed me this, I'd like to show everyone else. Is that okay? Okay. So Anuj came up to me, I think last week or at some point, and just wanted to confirm that he was kind of understanding what this first or fundamental theorem of calculus was telling us, like how an integral is related to some antiderivative value or connection. So I want to go over this in some visual way for us to make it click, perhaps. So I'm going to go ahead and take a look at some trig functions, just because those were the easy ones to graph, and that's what Anuj used as an example. So if you were to work backwards from cosine of x, what would your antiderivative be? Sine of x. Okay. And let's see. This cosine starts at 1, so this is my cosine graph, and this is my sine graph. Okay. So what if we were to look, I'm hoping I labeled these right, look at the interval from, Anuj, do you remember your interval?
I did.
Pi over 2 to 3 pi over 2?
Yeah.
Okay, so pi over 2 to 3 pi over 2. All right, so on this right-hand side, we know from the first fundamental theorem, after you work backwards, we do top bound minus bottom bound. So this would be sine of 3 pi over 2 minus sine of pi over 2. So what he wanted was a good visual to make this connection. On this side, the integral is representing the area under the cosine graph from pi over 2 to 3 pi over 2. So if we go from here to here, I don't know if that was your interval. I think it was pi to 2.
It was pi to 2.
Pi to 2 pi, my bad. We're going to change that up a little bit. All right, so the area under cosine graph from pi to 2 pi. So that's from here to here. We can shade below. We can shade above. What would that area value be?
0.
0, assuming I drew it accurately. We have the same amount of area below as we do above because it's a nice patterned cyclic wave. Okay, so the area, this is the area under the cosine x graph. Okay, we know that's 0. Notice how this should be equal to an antiderivative difference, okay, because we're subtracting. So you're looking at the difference of the antiderivative on that same interval. So sine of pi we know is 0, and sine of 2 pi is also 0. So the difference between those is 0. Good visual between the two. So the area under whatever this function is equal to the change in antiderivative value, okay, because we're subtracting two numbers together, essentially. Okay, that's the first, or the fundamental theorem of calculus, how we have an integral value equal to a change in antiderivative. Okay, so thanks to Anuj for sharing that with us. Okay, we're going to check this out a little bit more, but in relation to particle motion today, okay, relating this back to position, velocity, acceleration. So there are some things that we can probably keep in mind or just think about as we relate this back to particle motion. If you were to work backwards from velocity, wouldn't that represent position, like the previous function? And if we know the bounds from A to B, then we can plug in those bounds, doing top minus bottom, to get position at B minus position at A. This is our fundamental theorem of calculus, right? Work backwards and do top bound minus bottom bound. But let's think about this. This side is representing the area under the velocity graph. What does this side represent? You're essentially looking at a change in position from one point to another. Yes. Displacement, bless you, aka net distance. So this is what the fundamental theorem looks like algebraically, calculus-wise, mathematically. But we're essentially stating that the area under a velocity graph or a velocity function is representing the displacement of the particle on that interval. Now, what can get tricky is sometimes, maybe we'll draw a little picture here. Let's say this is our velocity graph. And I don't know, I'll make this 2 and 7. If I want to look at the area under this curve, notice how I can highlight this section, but also this one. What do you think the red area is representing? How'd you know? It's positive. Okay, so notice how velocity is positive, which means we're moving to the right, but the area under velocity is actually telling you how much you're moving to the right. Okay, a displacement, a change in value. So this is how much was moved right or up, okay, whatever direction we're looking at. So then what does the blue represent? Left or down, depending on the direction. Okay, so how much moved left? What's going on at 2? Change in direction. Okay, so stopped momentarily, because notice how the velocity is 0. Okay, you're not moving. Stopped momentarily and change direction. All right, so if I wanted to figure out how far a particle moved on the interval from 0 to 5, okay, I can just simply integrate, look at the area under the curve. But what if I wanted the total distance? I have some area moved right, some area or amount moved left. How would you get total? What do you think, Griffin? Go ahead.
Wouldn't you just like add them instead of making the bottom negative, you take the absolute value and just add them?
Right, so when we're doing displacement, notice how this area is positive, this area is negative. So the direction actually matters in terms of our displacement value. If direction doesn't matter for total distance, because we're just looking at the amount moved, okay, not the direction, then we want to negate this negative, aka make it positive. And we can do that by using an absolute value, because doesn't that change anything negative to a positive? So if we're looking for total distance, we actually want the area under the velocity curve with an absolute value taken. So can we think about how this graph might change if I apply an absolute value to it? If it changes anything negative, positive? Yeah.
The curve that like went after 2, whenever it goes negative, it would just like reflect over
It would reflect and then go this way. Okay, so if I wanted the total distance from 0 to 5, notice how I'd have positive and then positive again for that total distance. So if it's asking for total, we're going to take an absolute value, maybe reflect any negative areas. But if it's displacement, that direction is important. So we're going to keep the velocity, the positive and negative, the way it actually is stated on a graph. Okay, so we have to keep kind of these three things in mind. Let's go ahead and just try some examples to let this particle, we did a lot with particle motion for derivatives, but now we're going to bring that back for these integrals, okay, to help us perhaps work backwards. So the velocity of a particle is moving along the x-axis given by this function. Okay, no calculator for this one. if the position of the particle at time 4 is 72, what's the position at time 2? Can we discuss a game plan for this? And off the top of my head, I can think about maybe 2 different ways we can approach this, but I'm curious as to what we kind of feel like doing first. Okay, Kaden?
Find the antiderivative and plug in.
Okay, so find the antiderivative and then plug in what?
The 4 and 72.
The 4 and 72. Okay, so very similar to how we found the value of c, okay, to help us get the appropriate antiderivative function. Maybe we can do that here. So if we work backwards from velocity, don't forget the dt on the end, okay, that should give us our position function. So let's see, this would be t cubed plus 6t plus c. All right, this is our P of t position equation. So Kaden mentioned we know at time 4 the position is 72. So if you plug in 4 for those t's and set it equal to 72, we could probably figure out what c is. 4 cubed, 64, 6 times 4, 24. All right, solving for c. 72 minus 88. Say it again. Negative 16. All right, so our position function, t cubed plus 6t minus 16. I love it so far, but I'm not sure if we're done yet. What do we have to do next? Plug in 2. All right, so 2 cubed is 8, plus 12 is 20, minus 16 is 4. All right, so there's our position at time 2. Can we perhaps think about of a different method or a different technique to help us find the same value? That's why I sectioned it off. We'll try a different way, give you some options. What do you think?
Can you do the integral with like the interval of 2 and 4?
Uh-huh. Okay, so notice how they're giving us some function that we definitely have to work backwards from. They give us a t value to find. Well, actually, they give us the t value too, but they want the position at this t value, but they give us another t value of a position that we know. So if we work backwards from velocity, that should represent position. And if we do our fundamental theorem, we would do the top bound minus the bottom bound. Okay, a different setup. So in this one, we're solving for c, which we could do, or maybe we can use a fundamental theorem of calculus. If we work backwards, we'll have t cubed plus 6t. And on the right-hand side, we know P of 4, which is 72. And we're trying to figure out P of 2. So if we use the fundamental theorem over here, we'll plug in the top bound first. So if we plug in 4, we'll get 64 plus 24 minus, plugging in the bottom bound, 8 plus 12. So 88 minus 20 is 68. Can we figure out what P of 2 is? Pretty sure. We'd have to subtract 72 and then move a negative over. So that would end up being 4. Okay, notice how we get the same thing. Can we think about, though, what this 68 is representing? We know this c is just some constant term on the end of an antiderivative, but maybe this 68 represents something special. If it's the area under velocity from 2 to 4. What do you think, Anuj?
Is it the net distance that you traveled from 2 to 4?
That's your displacement. Yep, how much you traveled on some interval. So displacement from 2 to 4. I'll get in a little bit. Okay. All right, so let's see if this makes sense. They're telling us that the displacement from 2 to 4 is 68. Notice how at time 4 we're at 72, and we would have to subtract this displacement because the time value that we want to find, isn't that in the past? Isn't that before time 4? So if you're at this position at time 4 and this is how much you moved, then we'd have to subtract that in this case to get our position at time 2. Okay, so we have different ways to approach it depending on what you see first, what you're comfortable with. Sometimes though we're not going to have these two options. Like sometimes we'll only be able to use the C, sometimes we'll only be able to use the fundamental theorem, but it depends on what information we have. Okay, and we'll take a look at some of those, but at least for this one we had choices. What about B? What is the total distance of the particle on the interval from 0 to 7? Can we set up an integral to help us with that? What would it look like? Absolute value of velocity, and then our bounds are from 0 to 7. Okay. Now, we don't know how to work backwards from an absolute value. Okay, that's something that we do in higher calculus courses, but we can at least think about it. So can we visualize, okay, I'll go back to this graph, if there's a spot here where the velocity is going to change sign, either from positive to negative. Because if there is, then we're going to have to break it up into two separate intervals to kind of analyze separately. So if you were to think about the graph of 3t squared plus 6, only on the interval from 0 to 7, is there a spot where this would change sign? Obviously, if we plug in 0, we're going to get 6. Is there any other number between 0 and 7 that you can plug in here that would give you a negative number? No. So that's telling us what? Velocity is constant, not necessarily constant.
No, it doesn't change that direction.
Consistently positive. Okay. So V of t is always positive on the interval. Okay. So basically, if there's no change in direction, then, and if it's always positive, our area is always going to be above the x-axis. So essentially, these absolute value bars are not needed because they're not going to do anything. There's no negative number there to actually take the absolute value of. So I'll say absolute value not needed, at least for this example. But if there was a changing spot, we'd have to take that into consideration. All right, so basically, maybe we'll, I don't know, we'll leave the absolute value bars in there, but we'll just say this is the same thing as actually not having the bars there, okay, for this case. So since we're always positive, or the velocity is always positive, the displacement is actually the same as the total distance. That's what this statement is saying. So let's work backwards. This would be t cubed plus 6t. And we're going from 0 to 7. Oh gosh, can we do this without a calculator? 7 cubed 7 times 7 is 49 times another 7. Look at you. 343. 7 times 6, 42. Minus what we get when we plug in 0, that's going to be 0. So 343 plus 42, 385. So actually that's our displacement on the interval, but also our total distance because we never changed direction. We doing okay? We're relating these integrals back to particle motion. Let's perhaps try one that deals with a calculator. All right, we'll flip the page. The velocity of a particle moving along the x-axis is given by this function. If the position of the particle at 1.5 is 2.551, what's the position at 3.5? Okay, so it's actually the same type of question. I'm going to flip my page for a second. It's the same type of question that we had previously, but we did not have a calculator for this one. Can you think about which technique here might be more appropriate? We can either work backwards by hand and use the point to help us find C, or we can work backwards using the fundamental theorem and looking at this change in position on the right hand side. Can we think about which technique would be more appropriate? I'll flip it back. Do you feel like working backwards from this by hand? No. Okay, that would be very, very difficult. Okay, so this one I think would be more appropriate to use the bound idea instead of solving for C. So our lower bound is 1.5, our upper bound is 3.5. I'm going to write in my velocity function. And according to the first fundamental theorem, if I work backwards from velocity, that's going to represent position. And since I know the bounds, I can plug in my top bound first and then subtract, plugging in my bottom bound. Now I know in the last example we did this piece by hand because we didn't have a calculator. But now that we do, can we figure out this left-hand side? Do we remember what buttons to press to type in an integral?
Math.
No?
Math 9.
Math 9. All right, Math 9. Lower bound 1.5, upper bound 3.5. And we'll type in our velocity function. 0.5 e to the x. I know it's t's on your paper, but it could be x in your calculator. And then the rest. All right, 15.91919. Remember, we don't round to 4 decimals till the very, very end. Okay. Can we get the same thing? Yeah?
Do we put X in a little D spot?
Yes. I know it's T on your paper, but it'll be X on your calculator. Okay, so this is representing, since we worked backwards from velocity, this is representing a change in position from 1.5 to 3.5. So at 1.5, we're at 2.551. What do you think we have to do with this change to get us to the position at 3.5? This is where we start. This is how much we move.
Keep going right.
Yep, so we're gonna add it. Okay, so we can kind of see that if we do position of 3.5 on the right side of our equation, we're essentially subtracting 2.551 here. Wouldn't we have to add that over to the other side to get our position location at 3? All right, so if I add 2.551, we'll get 18.9 0.470. All right, so like I said, when we don't have a calculator, that usually means the functions are easier to use, meaning we could probably work backwards by hand. So you do have some options on how you want to do that or how you can do that. If it's calculator active though, odds are the functions are more involved, which means working by hand backwards is going to be very difficult. So I suggest using your calculator to help you with those. Okay? We doing okay? All right, let's try the next one. Very similar, total distance. So we'll have the interval from 1 to 5, and we need the absolute value of velocity. Now, unlike the first one that we kind of had to figure out, is there a spot where something changes? Since we're using a calculator, maybe we don't have to worry about that analysis because technically we should be able to type this in its entirety. The question is, do we know where the absolute value option is? Maybe. Well, let's first get the integral. So we'll do math 9. We'll type in the bounds 1 to 5. And then for the function spot, we have to type in the absolute value. Are we familiar with where to get that from? No? Okay, we're going to go back to math. This time scroll over to number, N-U-M at the top, and it's the first one, ABS. Abs, yep. So that should bring up the bars, and we're just going to type in the function inside of those. So you're basically telling your calculator, I don't know if there's a change in direction somewhere, but if there is, I want you to take that into consideration for this total distance. All right, and hit enter. So we'll get, it might think a little bit, 913.067. All right, I'm going to do something real quick. On my calculator, you don't have to do this. I'm going to type in another integral with the same bounds, but this time I'm not going to type in the bars. — 9112. What's the difference in meaning between those two numbers? It has to change direction somewhere, right? Because displacement and total distance are different. So this is just how much it moved from 1 to 5, strictly beginning to end. This is total distance, how far left, how far right, all added together. So there is some minuscule interval, like what there's only really a difference of about 1 here, where it did change direction for a short period or a short distance. Okay, so displacement, total distance, two separate things, okay, when you change direction at some point. So by analyzing those two, we know it changes direction somewhere. We don't know where. We're not going to find out. Okay, we could if we wanted to, but at least we know there is a change of direction at some point. All right, let's try some more. This time we'll take a graphical approach, not so much calculator involved. The graph of velocity, they give us units, feet per second. We're traveling along an x-axis. The position of a particle at 8 is 12. Use the graph to answer the following questions. What is the position of the particle at time 3? So unlike the previous examples, we do not have a physical equation to work backwards from. We only have the graph of velocity to help us out. Can we perhaps set up an equation or an integral to help us with this? Or at least represent it? They give us velocity and they're asking us about position, so we know we're going to have to work backwards somehow. Can we fill in the rest of that integral?
From 3 to 8.
3 to 8, good. Okay, so a time we want to figure something out and a time that we know. We'll work backwards from velocity. All right, and let's fill in what this is going to represent. If we work backwards from velocity, we should represent something about position. And since we know the bounds, we can do top bound minus bottom bound. So on the left-hand side, this integral, even though it's representing a displacement for position, is also representing the area under the velocity graph, which we conveniently have. So if we want to go from 3 to 8, we have to figure out what all this area is. All right, can we use geometry to help us with that? Probably, what's our first shape?
It's a rectangle.
Okay, so you can do a rectangle and a triangle, break it up into 2 pieces, or overall, it's a trapezoid. So do whatever you're more comfortable with. I'll do trapezoid. So 1/2. Our base, okay, now this is tricky because notice how the parallel sides in this example are the top and the bottom. Okay, unlike the trapezoids that we drew under a curve when we did the Riemann sums. So our height is actually a height in this example of 5. And our base values are 1 and 3. So we'll add those together. Our next shape is a triangle, but notice how it's underneath the x-axis, so it should be represented as a negative amount. And we'll have 1/2 times the base of 2 times the height of 2. All right. Now on the right-hand side, we know P of 8 is 12, and we're trying to figure out P of 3. So I think we have a good setup to go from here. Let's see. 5 times 4 is 20. Half of that is 10. Minus 2 would be 8. So the area under velocity is 8. Okay, that's our displacement, how much we moved on this interval. So to solve for our position at time 3, we'd have to subtract the 12, but then move the negative. So we'll get 4. Can we put a unit on it? Feet. There we go. Again, let's see if it makes sense. We know at time 8, our position is 12. From the integral, we know our displacement is 8. Since they're asking us about a time in the past, okay, time 3 compared to time 8, doesn't it make sense that we have to take this position at 12 and subtract the displacement to see where we were previously? So 12 minus 8 just confirms the 4 that we found. Okay, we'll stop there for today. We'll go ahead and move on with the other ones tomorrow.